Hey folks, welcome to this episode on solubility. So, when we were looking at our single displacement reactions, we used something called the activity series to predict whether or not the reaction would happen, aka whether that lone metal would actually have enough reactivity or activity to replace the ion in solution. When we're dealing with double displacement reactions, what we're going to be looking at is something called solubility and the rules that are associated with solubility. We're going to use this to help us predict whether or not these double displacement reactions will actually happen. In this case, where we have lead 2 nitrate reacting with potassium chloride, we do have a reaction that's occurring. And you can see that here we have aqueous, 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 and solid, which is going to be what we're going to be talking about in a little bit. But here, when we have this reaction, the only thing that we've changed is with a chloride into a chlorate. We have no reaction. And that really is because the products, and I'll use kind of quotation marks around products, are both going to be in the aqueous state. So when you have products both in the aqueous state, it actually means that no reaction has actually happened. There are going to be some rules that will dictate what is a double displacement reaction and how we know whether or not it has occurred. So just to highlight solubility for a little bit, remember what solubility means and the kind of definitions. Remember that a solute is something that is being dissolved in a solvent to produce a solution. So this could be in the state of solid, this could be liquid water, and this would be an aqueous solution because we have this solute dissolved in water, and so we'd have an aqueous solution of whatever that solute would be. Now, solubility is really just the amount of solute that can be dissolved in a given quantity of solvent at a given temperature. Temperature and pressure are both determinants of the solubility. But if we look at, for example, this little case, let's look at ammonium chloride, NH4Cl, and we can use this little solubility graph to show the what happens to the solubility of these compounds as we increase the temperature. So if we find ammonium chloride, which is this purple line over here, at 70 degrees, for example, we can find 70 degrees. We bring it to that line, okay, and wherever that line is, we go across. So it's just above 61 grams of solute dissolved in 100 grams of water. Now, when we talk about density of water, it's 1 gram per milliliter of water. So we can also say, so 100 grams is equal to 100 milliliters of when we're talking about water. So that's why we can state it as 100 milliliters instead of 100 grams. Sometimes you'll see it as grams, sometimes you'll see it as milliliters. But we're going to be working with this chart as we go on later on in our course. But we're just trying to highlight what solubility is at the moment. Now, when something is dissolved, it could be soluble, completely soluble. It could be partially soluble or slightly soluble. And then sometimes it doesn't dissolve, or it doesn't really dissolve a lot, and that is called insoluble. So these are the differences between these different solubility amounts. What we define soluble is that when we can add more than 1 gram of solute in 100 milliliters of water. And as we go to less soluble or insoluble, that amount gets a lot smaller. So when we're talking about insoluble, it doesn't actually mean that no solute dissolves. There usually will be a very, very small amount, and that's the key, that it's very, 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 very small amount, almost unnoticeable. But the solubility is really a relative term. So again, here 1 gram, here is between 1 gram and 0.1, and here is less than 1 gram. Now, as we get into our stoichiometry unit, we're going to be looking at moles per liter. So just keep this in mind, and we will revisit that a little bit later. Now, this looks very, very complicated, and these are the solubility rules for these ionic compounds in water, and it's usually around 20 degrees Celsius. Again, remember that temperature affects the solubility. So these are usually stated at about 20 degrees Celsius. So when we look at these, this is kind of split up into two sections. It says that these compounds are generally soluble. So things that contain lithium, sodium, potassium, and ammonium are usually soluble, and there's not really any exceptions. Things that contain nitrates and acetates are also very soluble, not really any exceptions. Chlorides, bromides, and iodides are generally soluble, but there are some exceptions. If silver was to bond with any of these three, or a mercury or lead 2 to bond with the chloride, bromide, and iodine, that would create an insoluble compound. So other than those, any other metal that bonds with these, for example, if we took potassium and iodide, that would be an aqueous solution. It could be soluble. But if we had something like lead to iodide, PbI2, we're going to get this kind of very yellow, solid-looking precipitate or solid. Again, sulfates, SO4 2 minus, is usually soluble except when it's paired with these elements there, creating insoluble compounds. On the second part here, we're looking at is things that are generally insoluble. Okay, insoluble. So a very, very, very tiny amount of it dissolves, but for our purposes, we're just going to say it doesn't really dissolve. Hydroxide and sulfides are generally insoluble, but there are some exceptions. Again, if you're bonding with these lithium, sodium, potassium, or ammonium, these ones over here, you're going to get a soluble compound. Same thing with some group 2 metals, you might get a soluble compound when you're dealing with the sulfides. With the OH, if you bond with those exact same compounds, you'll get something that's slightly soluble. So some of it will dissolve, some of it won't. You'll get that kind of medium definition that we had before. Same thing with the carbonates and phosphates. Usually when you bond with these ones, the group 1 metals and ammonium, you'll get something that is soluble. So this is a very, very hard thing to memorize. There are different mnemonics that will help you memorize that, but there's also something that we've done that makes things a little bit easier. We've created something called a solubility table, and it just organizes these rules that you saw in the previous one to allow for an easy way of predicting whether or not a compound is soluble in water. So basically, to predict whether or not something is, if let's say, for example, we have a compound, let's say we have copper 2 carbonate, so that would be CuCO3. Now we want to figure out what the state is over here because that's part of our creation of our formula. So the first thing we want to do is we want to find our cation. Okay, so our cation in our vertical column is here. So there's our cation, copper 2. Okay, and carbonate, our second step is in our horizontal. And we look at this. So where these lines intersect is our state. Now here it says I, and that stands for insoluble. So if something is insoluble, what state will it be in? Well, that means it will be solid. So here, let's see if we can predict the solubility of these aqueous compounds. So here we have ammonium and carbonates. So again, let's just find our ammonium is over here, carbonate is over here, and we have S. So S stands for soluble, and if something is soluble, that means it's going to be in the aqueous state. So we have aqueous there. AgCl, here we have silver over here. And Cl with chloride. So again, right over here is where we're looking, and it says I, which is insoluble, and that means it's going to be in a solid state. Okay. So again, here are just some of the terms that we see. Different charts will have different terms or different letters or combinations of letters for the terms. S is generally soluble. I is insoluble. Again, it's a very small amount that will dissolve. The rest of it will precipitate out. So generally when we say it's insoluble, it's going to be solid. The confusion here is partially soluble. It also means that a small amount will dissolve, the rest will precipitate out. And generally we say that is solid when we look at it. But it does differ. Some people will say aqueous, some people say solid. Once you get into the grade 12, you're going to be looking at something called KSP, and that's going to be actually giving you a value of how much it actually dissolves. So right now we're limited to kind of almost three different states. Later on we can put a numerical value onto how much it actually dissolves. We might have things that decompose, so they form more stable compounds. It might be that a copper 2 turns into a copper 1, for example. It's a little bit more stable, so it might break down. And sometimes you'll see blanks or little hyphens. These don't exist, or AKA cannot be isolated. So they might exist in solution, but when we try to isolate them, we can't really do that. So pause this video now, and using the solubility table that you have, try to predict whether or not these are soluble, insoluble, partially soluble, and try to figure out what the states are. So go ahead, pause the video now, we'll be back with the answers. So welcome back, here are your answers. In the first case we have iron 2 nitrate, so to figure out what we're looking for on the actual table, we have to break them up into the ions. We have Fe2+, so that would be on the table, usually it will be as Fe2. And then we have nitrate over here, so if we look at our columns, we look at one and the other, we'll usually come up with S, which is soluble, so that means that this compound will be aqueous. Chromium hydroxide, again, here's our formula, and we see that it is insoluble, so it exists as a solid. Aluminum bromide, again, bromide is usually things that it's going to be soluble, so again, we have an aqueous format. Mercury and chloride, so that was one of our exceptions when we had BrClI. If it reacts with the mercury, it could be insoluble. So in this case, it's only partially soluble. We're going to consider it as a solid. And again, here we have an insoluble compound of calcium phosphate. So we have the state of solid. There are other solubility rules. We're going to be focusing on this a little bit later on in the course, where we look at the solubility of gases. It's interesting that as temperature increases with solids, the solubility usually increases. With gases, as we decrease the temperature, the solubility of gases increase. So it's a little bit different from solids, and we'll talk about that a little bit later. Strong acids and bases, they dissolve in water. So acids, remember, acids are something that contain a hydrogen that breaks off. So for example, if we have HCl, that's going to break off into H plus and CO minus when it goes in water, and these are both going to be aqueous. Okay. And a base, for example, LiOH, that's going to break up into Li plus, and that's going to be aqueous, and OH minus, again, that's going to be aqueous. So those dissolve in water. And it's actually interesting that water actually kind of dissolves in itself. This is a kind of forward and reverse reaction. It's called auto-ionization of water. And as when you get into grade 12, you look at, and it's going to be a little bit different than this formula, but water actually breaks up and then reforms, breaks up and reforms. So thanks very much for watching. See you next time.